Working as a quant, you're typically going to be dealing with very large amounts of data. The purpose of our Week 5 lecture here is to introduce some basic ideas about algorithm performance, what big O notation is about, and also we'll take a look at some sorting algorithms, which of course are useful in and of themselves and will also give us a chance to look at algorithm performance analysis. We're going to start out by taking a look at the performance of some common searching algorithms. Let's suppose that we have some unordered sequence of values. We know how many values we have. We know that they're all, let's say, int values or float values. But we don't know anything at all about the ordering of these values. And we need to search within the sequence for some particular value j. Now, because we don't know anything about the relative ordering of these values, what we're going to have to do is to check each value in the sequence v until one of two things happens. Either we discover a value in v that is a match for j, and in our case we're simply going to return true then, indicating that the value j does exist within the sequence v. Or if we run out of all of the possible values in v and we haven't found j, we'll return false. This business of checking each value in the sequence, one value at a time, gives us what's called a linear search. And it should be clear, although I've put clear in quotes here, that if you double the amount of data that you have to search through, this should also double the average search time looking for a particular value j. In Python code, here's an implementation of the linear search algorithm. As the first argument, we have our sequence that we're calling v, and the second argument is the value that we're looking for, j, within v. We're using a for loop to implement this linear search. For each val in the sequence v, if val is equal to the value that we're looking for, j, then we're done and we can return true at that point. On the other hand, if we make it all the way through v and have not found j and return true, then we will return false. Next, let's suppose that instead of having an unordered sequence of values, we have instead a sorted sequence of values. And we're going to assume that we have them in a non-descending order now in our sequence v. Once again, we need to search for some particular value j within this sorted sequence v. Since we know that the values are sorted, we can use what's called a binary search, at which we cut in half at each iteration the amount of data in the sequence v that we still have to look at. So we will figure out what the midpoint of our sequence v is, and if the particular value in the sequence at that midpoint is less than the value that we're looking for, that implies that the value that we're looking for, if it exists at all, must be to the right of the midpoint. Okay, so if the value at the midpoint is less than j, we will continue looking for j in the right-hand half of the sequence. Otherwise, we'll look to the left. Now, we repeat this procedure, and we can do this either iteratively or recursively, until we get down to having a one-item wide subsequence of v. At that point, if that particular value happens to equal j, we'll return true. Otherwise, if that particular value is not equal to j, we'll return false. Now, during each iteration of this loop, we will reduce the remaining number of items in v that we have to look at in half. So I hope that it's clear, although we have clear in exclamations here, that if you double the length of the data that we have to look through, then we're only going to have one more step in our iteration or recursion to narrow down to find that particular item, or fail to find that particular item, j. Here on slide 5, we have some example code for implementing this binary search. within an ordered sequence V, we're going to start by setting low and high indices for accessing the initial element and the final element in our sequence V. Let's suppose our sequence V had 10 items in it. Then the low index would be 0, and the high index for a 10-item sequence would be 9. All right, now, until we get to the point where the low index and the high index are the same, we need to find the midpoint between the low index and the high index. In our particular example, where we've decided that our sequence V has 10 items in it, 9 plus 0 over 2 is going to give us a mathematical midpoint of 4.5. But there is no item sub 4.5 in this sequence V, so we're going to use floor division to, in effect, round down to 4. All right? So we will compare the value at V sub 4 to see whether that's less than j. If the value of V sub 4 is less than j, that implies that the value j, if it exists at all, is in the right-hand part of V. So what we're going to do is to increase our low index by mid plus 1. Now, the reason we're adding 1 to the low index is because we rounded down the index when we computed the midpoint. On the other hand, if the value at the midpoint that we initially computed is greater than or equal to j, we're simply going to drop the high index down to the midpoint. Each time through this loop, we are either going to increase low to mid plus 1 or decrease high to mid, so that we will definitely get to a point where low is equal to high. When we get to the point where low is equal to high, we will compare whether that item in the sequence is equal to j. If that item in the sequence is equal to j, we can return true, otherwise we'll return false. Here I'm using an inline if-else expression to make this decision about whether to return true or false. This inline if-else was described in one of the homeworks. Now, let's suppose that our collection of values that we need to search is stored in a set rather than in an unordered sequence or an ordered sequence. It turns out that a set in Python is implemented as something called a hash table. And the hash table has a very important property that when you search for a particular value within the hash table, it always takes exactly the same amount of time to determine whether that value is in the hash table or not. So this is going to be true whether the hash table has one element in it or a million elements in it. When you search for a particular value in the hash table, it always takes the same amount of time to do that search. So in this case, although I have not described at all how you create this magical thing called a hash table, I hope it's clear that if we double the size of the set V, that is the hash table V, that this is not going to change the search time when we're looking for a particular item value j. Since the Python language provides set to us, implementing a search in a set is trivial. We have our set as the first parameter to set search, and the value that we're looking for, j, as the second parameter, and we simply ask whether j is in S, using the built-in in operator for sets. This will yield true if j is in S and false otherwise, so we'll simply return whatever value we get from in. Okay, so we've now taken a look at implementations for a linear search if we don't know anything about the ordering of the values in the sequence we have to look through, or a binary search if we do know that the values in the sequence are ordered, or finally, a hash table or set search if we know that our values are stored in a hash table, or in Python's case, a set. So let's take a look at some example code we can use for testing the relative performance of these various algorithms. Here on the right is the searches.py file that's available to you on Canvas. In the top part of the file, we have our three definitions of linear search, binary search, and set search. Now we're going to want to import NumPy so that we can use its random number generation facilities. And of course, we'll import that with the abbreviation NP. Initially, we're going to have a relatively small data set that we're going to search for values in. The length of this data set is going to be just 1,000. Next, we want to get 1,000 random integers from some uniform distribution of possible integer values, so that we don't have any biased understanding of the relative frequencies of various possible values in this data set. randint lets me allocate an ND array of random integers from a uniform distribution. The lowest possible value in this distribution is 0, and the value 1 past the highest possible value I'm going to set as 2 billion. I happen to know that in an int32, which is the integer type within this ND array, the maximum possible value that will fit into an int32 is a little bit over 2 billion. So I'm going to have possible values generated in this uniform distribution between 0 and 1 less than 2 billion. Notice here, by the way, a new feature I've tossed in, which is if you have a large integer value, or for that matter, a large floating point value, to make the value easier to read, you can throw underscores in wherever you wish. Here I've chosen to throw underscores in to separate 2 billion, where I might otherwise have used commas in a written document. The keyword parameter size specifies how many items there should be in this random ND array of ints, and this is going to be vlen because I want 1,000 values in this random sequence. Okay, now from those 1,000 random int values between 0 and 1 less than 2 billion, I want to create 3 data sets to test my 3 algorithms. The first data set I want is going to be an unordered sequence, and for that I'll simply make a copy of the raw collection of 1,000 integers that I got from randint. The next set I want is a sorted ND array. For that, I can simply use the .sort method on the raw data that I got from randint. And then finally, I want a set of these values. And because an ND array is an iterable, I can simply use my set construction function to build a set of those values. Now, this set might actually contain 1,000 values, but it's also possible that there were some duplicates produced by randint, and therefore it's possible that this set might be smaller than 1,000 values. Now that I have my data sets generated, I want to perform searches within that data set. Doing one search within a data set of 1,000 values is going to take almost no time, regardless of how bad my search algorithm is. I'm not really interested in knowing how long it takes to do one search for one value in this data set. I want to be able to compare the relative lengths of times that it takes to do a linear search versus a binary search versus a hash table search or a set search. So instead of just doing one search, I'm going to do 100,000 searches. And I'm going to do 100,000 searches for random integers in the same uniform distribution that I drew my data set from. Okay, so my data set is 1,000 uniformly distributed random integers between 0 and 1 less than 2 billion. And my sample for searching is going to be 100,000 integers drawn from that same distribution. We can try to compute very accurate timings using a facility in Python called timeit, but timeit is extremely fussy. So instead of that, since we're using 100,000 searches, we're going to get times that are big enough for doing relative comparisons using a somewhat less precise timing mechanism. We're going to import the time module, and within the time module, there is a time function that produces the number of seconds that have elapsed since midnight, January 1st, 1970. Let me show you an example of that in my shell. I'm going to import time, and then from that time module, I'm going to call the time function. These are the number of seconds that have elapsed since midnight at the beginning of January 1st, 1970. And if I ask for the time again, I will see that more time has elapsed, a little over 12 seconds. So in order to determine how long it takes to do something, I can save the time at the beginning, and I can save the time at the end, and then I can compute the difference between those two times. That will give me an approximate but pretty reasonable duration for how long it takes to do something. In this case, the something that I'm doing is a search. First, I'm going to do a linear search. So, I will save the time at the beginning before I do my search. Then, for each possible value in my samples of 100,000 values for j, I'm going to do a linear search in the unordered sequence for the value of j. Now, linear search is going to return to me either true or false, but for timing purposes, I don't actually care what value I get. I don't really care whether j was found or not found, because I'm only interested in knowing how long did it take to do the search. All right, so I'm going to do 100,000 linear searches in this unordered sequence. I will then save the time at the end of that 100,000 linear searches so that I can compute the elapsed time in seconds for those linear searches. I'll do the same thing for binary searches within the sorted sequence and for set searches or hash table searches within the set. When I'm all done doing my 100,000 linear searches, my 100,000 binary searches, and my 100,000 set searches, I can then display the elapsed time that the linear searches took, the elapsed time that the binary searches took, and the elapsed times that the hash table searches took in a convenient format. Now, in fact, my searches code does this not only for a 1,000 item sequence, but then we double the number of values in the sequence until we actually get up to a little over 2 million values in the sequence. So this so-called V factor is going to start at 1, and I'll therefore start with a sequence of 1,000 values, but then each time through my loop, I'm going to double that V factor. So then I'll do it for 2,000, then I'll do it for 4,000, then I'll do it for 8,000, all the way up to 2,048,000 values in my data set. Okay, so here's the complete code, and let's take a look at the output that I got on my system. Now, for my system, doing 100,000 searches in a 1,000 value sequence or set, I got a little over 6 seconds for 100,000 linear searches, a little less than a quarter of a second for 100,000 binary searches in the same collection of values, and not quite 0.02 seconds for hash table searches, 100,000 hash table searches within a set of those 1,000 values. Okay, so we see that the linear search is a lot slower than the binary search, which in turn is a lot slower than a hash table search. That's useful information to have, but even more useful is what are the trends of the times for these different searches as the size of the data set that we're searching through increases. That is, if the size of our data set goes from 1,000 items to 2 million items, and the linear search is sitting at around 7 seconds, whereas the hash table search balloons up to 1,000 seconds, let's say, well, then we know that the linear search is bad for this small data set, but it's actually much better for a really big data set. It won't surprise you to learn that the opposite is the case. Here's the results that I got on slide 12 as I kept doubling the size of the search data set. Every time I doubled the size of my data set, the amount of seconds taken for the linear search also approximately doubled. All right, so I went from 6 to 12.5 to 25 to 50, etc., etc. That is, I had a linear increase in the search time as compared with the size of the data set that I was searching within. Now, the binary search on a sorted data set, it's not too obvious just glancing at this table, but more or less, the incremental time going from size 1 to size 2 to size 4 to size 8 is approximately the same. It's approximately an equal amount of time going from 1 to 2 as it is going from 2 to 4, as it is going from 4 to 8. If the size of the data set is doubling, and the amount of time that it takes to do a search is increasing by a roughly constant amount, then this gives us what's called a logarithmic increase in search times. Finally, for our set searches, our hash table searches, we claim that the time to do a hash table search should never change. Well, in reality, it did change some, but it didn't change very much. We went from approximately 0.02 seconds to approximately 0.03 seconds as the size of the data set we're searching in increased by a factor of 2,000. So for our set, this isn't exactly constant, but it's really pretty close. Okay, I've converted these into graphs that we can look at. So here's what happens if we apply a linear search to a set of data. No surprise, we got a line. Each time we double the amount of data, we also double the amount of time. Or more generally, if we increase the amount of data by a factor of n, we also increase the amount of time by a factor of n. And this is called an order n algorithm. We increase the data by a factor of n, we increase the time by a factor of n. Here's what the binary search looks like. It's not exactly the case, but if you look at these dots representing the actual timings for the different size data sets, you can see that the increment of time going from a set of 1,000 to 2,000 is pretty similar to the increment of time going from 2,000 to 4,000, or from 4,000 to 8, or 8 to 16. So each vertical step here is roughly the same distance as we doubled and doubled and doubled and doubled the amount of data. In fact, if I convert the data set size axis to a logarithmic axis, which I've done on slide 15, we'll see that now we get something that does look approximately like a line. It's not a perfect line, but we do have randomness in our data. I am running on a system that has multiple applications running at the same time, so it's not perfect, but we can see that it is approximately a line on a logarithmic scale, and therefore this is an example of what's called an order log n algorithm. Increasing by log n as the data set size increases is significantly better than increasing by n as the data set size increases. So binary search, as you won't be surprised, is significantly better than linear search, particularly as the amount of data increases. Finally, hash table searches are the best of all. Now, this is not exactly a flat line as we would hope for a perfect hash table, but we'll say it's pretty flat. So a hash table search, where the amount of time taken to do searches does not change, is what's called an order 1 search. That is, if you double the amount of data that you're searching through, you don't increase by the log of that increase, and certainly nothing like by the same factor as the increase. Instead, you remain pretty much at a flat amount of time. Okay, so those are some live examples of the order n performance that you get from linear search on unordered data versus the order log n performance that you get from a binary search on sorted data versus the order 1 search that you get on hash table lookups, or sets in the case of Python. Okay, so by doing a little bit of reasoning and by looking at some examples, we've seen that if you do a linear search through an unordered sequence, that is order n performance. That is, as the size of your data set increases by a factor of n, the time that it's going to take to search through that data set is also going to increase by a factor of n. This is not really very good performance, although relatively speaking, it isn't horrible. Now, if you're lucky enough to have a sorted data set, then you can, if you're doing searches, apply a binary search. That gives you order log n performance, which means that as the size of your data set doubles, the amount of time it takes to process that data only increases by a constant interval. And that is actually really good. In fact, even if your data set gets to be hugely, hugely gigantic, the log of the number of items that you have in that data set is going to remain pretty small. For example, the binary log of 1,000 is about 10. The binary log of 1,000,000 is about 20. The binary log of 1,000,000,000 is about 30. You can see that you can get up to really, really vast data sets, and the binary log of the size of that data set is probably going to remain less than 100 in real-life examples. Now, best of all, except that you have to have a hash table for this kind of performance, is order 1 performance, where the performance, the search time, does not increase noticeably, if at all, as the size of your data set gets larger and larger and larger. Okay, well, this is all just intuitive and experiential with just a little bit of analysis behind it. We really need to formalize what the definition of big O is and how you go about evaluating the performance of arbitrary algorithms. Okay, so basically we have some function that describes in a reasonably precise way the amount of time that it's going to take for some algorithm to run based on the size of the data set n. And for big O notation, and here I'm talking about the academic definition of big O, what we want to find is some other function, g of n, that acts as an upper bound on f of n that describes our specific algorithm. And we'd like the form of g of n to be simple, something like log n or n squared or n cubed or n log n, something that's relatively easy to express, even if f of n itself is fairly complicated. Okay, so we're going to say that fn is big O of some bounding function g of n if there's some value n0 for the data set size greater than or equal to 0, and if we can find some positive constant such that the function that accurately describes the performance of our algorithm is always less than or equal to that constant times g of n for every value of n greater than n naught. Okay, that is, once our data set gets to be a certain size, n naught, if it grows beyond n naught, it's guaranteed that the precise amount of time it takes to perform that algorithm, f of n, is bounded above by this upper bound function, g of n, with some constant in front of it, some positive constant in front of it. If I reduce this to mathematical notation, we're saying that f of n is big O of g of n if we can find a constant c greater than 0 and some integer n not greater than or equal to 0, such that f of n is less than or equal to cg of n for all n greater than n naught. Well, let's take a look at an example. Suppose that we have some algorithm like this. There is some operation that we need to perform in this algorithm over and over again, and this operation takes some positive amount of time t. Our program looks like so. We do the operation once to initialize the program. Then we have a for loop that loops 4 times, containing an inner for loop that loops n times, in turn containing another inner for loop that loops n times, and the operation is being evaluated within this doubly nested for loop. After that's done, we have a loop that runs 3 times, containing a loop that runs n times, performing an operation, and then we have one operation to finalize that. Now, the individual operation takes t amount of time. And if we have nested loops, and the innermost part is that operation that takes t amount of time, then this doubly nested loop is going to perform that operation 4 times n times n times. So the operation is going to be performed 4n squared times in that loop. In the next loop, which is nested, we're going to perform the operation 3n times. So what we have here is 1 plus 4n squared plus 3n plus 1 times that we're going to perform this operation that takes time t. All right, so we can write that down like so. The approximate amount of time that this algorithm is going to take is whatever t is times 1 plus 4n squared plus 3n plus 1, which we can reduce to t times 4n squared plus 3n plus 2. Now notice what happens here is the amount of data increases. As the amount of data increases, the time that it takes to perform the algorithm increases as a function of n. T is just really a constant in here that we can ignore for big O analysis, because in big O analysis, we're not really interested in the precise amount of time an algorithm takes. We're interested in knowing how much worse is the time of that algorithm going to get as the size of our data increases by a factor of n. Okay, so we will say that f of n here, describing the rate of increase as n increases, is 4n squared plus 3n plus 2. And our question now is, can we find a g of n that is an upper bound for f of n? And at this point, that seems like almost a silly question, because obviously we can find some function, g of n, that's going to be greater than 4n squared plus 3n plus 2 beyond some specific value n naught for capital N here. Let's suppose as a candidate that we define g of n to be n cubed. And as a candidate, let's pick c equal to 1, which is a constant greater than 0. All right, so we can specify the size of our data set, and then we can compute f of n and g of n. Well, if the size of the data set is 1, then f of n, it turns out, computes to 9, whereas g of n, which is just n cubed, computes to 1. So we don't yet have g of n as an upper bound. But as our data set size grows, g of n starts catching up with f of n, and once we get to n naught equal to 5, we see that g of n cubed, has surpassed 4n squared plus 3n plus 2, and beyond that value of n not equal to 5, it's easy to see that g of n, that is n cubed, is always going to be bigger than f of n, 4n squared plus 3n plus 2. So we can say that n cubed is an upper bound on this quadratic expression, 4n squared plus 3n plus 2. Well, this is really no surprise. If we have any quadratic expression producing a positive value for all possible values of n greater than 0, then it's pretty clear that we just have to find an n naught big enough, and n cubed is going to be bigger than that quadratic expression. Okay, well, we're only about 1/3 of the way there, so let's continue. Next, we're going to define big omega, which gives us a way of determining a lower bound on our timing function f of n. All right, so we're going to say that f of n is big omega of g of n if we can find some n naught greater than or equal to 0 and some constant greater than 0, such that f of n is always greater than or equal to c times g of n for n greater than or equal to n naught. So here we have that g of n is a lower bound of f of n. The mathematical expression of this is the same as for big O, except that we have a greater than or equal to symbol here, rather than a less than or equal to symbol as we had in big O. So let's take a look at this. Well, same program, so f of n is the same. The time that it takes for our algorithm to run is going to grow as 4n squared plus 3n plus 2. Can we find a g of n such that f of n is big omega of g of n? Well, let's pick something really trivial. Let's just say g of n equals 1, regardless of the value of n. And we'll also pick the constant c to be 1 and n naught to be 1. Well, then it's trivially the case that 4n squared plus 3n plus 2 is always going to be greater than 2. It's therefore always going to be greater than or equal to 1 for every single value of n greater than 1. All right, so again, we have found a lower bound for f of n. And again, this is sort of a, who cares? All right, well, so here's the good part. Rather than finding a function g of n that's an upper bound, like n cubed in this case, and a separate g of n that's lower bound, like 1 in this case, can we find a single function g of n that serves as both an upper bound and a lower bound? That is, can we find a single g of n such that f of n is both big O of g of n and also big omega of g of n? That's what our actual goal is here. Okay, so we say that some function describing the runtime of an algorithm is big theta of some other function g of n if the function f of n is both big O of g of n and also big omega of g of n. That is, g of n serves as both an upper bound on f of n and as a lower bound on f of n. Now you might think, well, how can one function possibly serve as both an upper bound and a lower bound on some other function? The reason that we can do this is because of the way we defined big O and big omega. Remember that we have these constants involved that we multiply g of n by. And so we can, in fact, find a single g of n that can serve as both an upper bound and a lower bound by choosing different constants for the upper bound side and the lower bound side of the analysis. In our particular case, our f of n for our example algorithm is 4n squared plus 3n plus 2. Can we find a single g of n such that f of n is big theta of g of n? Well, in this case, we may have to scratch our heads a little bit, but the usual answer to finding g of n is to find the dominant term in f of n and ignore the constant in front of it. So the dominant term in f of n here, as n gets larger, is going to be the n squared part. So let's try having g of n be n squared. By looking at f of n, we can then discover that if I choose a constant of 9, f of n is always going to be less than or equal to 9 times n squared for all values of n greater than n naught equal to 1. And if I choose another constant, c2 of 1, then I discover that f of n is always greater than or equal to 1 times g of n. Consequently, we have discovered a single g of n, namely g of n equals n squared, such that f of n is big theta of g of n. Now, in industry, rather than using big theta, people tend to talk about big O, the order of an algorithm. And frankly, my guess would be as simple as people don't have a big theta on their keyboards, so they tend to use big O. It's very likely that you're going to be asked questions about algorithm analysis and about big O notation during some of your interviews. Okay, so let's summarize a bit what we know about big O. If you're searching in a hash table like a set, then the big O, or academically the big theta, for that is order 1. That is, the time never changes regardless of how big n is. If you're fortunate enough to have some sorted data, then you can do a binary search on the sorted data, and this will give you an order log n algorithm, which in real life is almost as good as order 1. A single loop where you step through all of the elements of some data is linear. That's going to be order n. This is kind of bad, but frequently the best that you can do. If you do find yourself needing to use a nested loop, you'll get order n squared performance. And as n gets larger, that gets much, much, much worse than linear performance in a big hurry. Order n cubed is really, really terrible. But there are situations where order n squared or order n cubed is the best known algorithm. And in such cases, if you can discover how to create an algorithm that performs the same job, but in order n log n time, or that finds solutions for an important subset of problems in order n squared time rather than order n cubed time, that will be a good way of getting yourself a PhD in computer science or machine learning. Or in quant finance, this can give you a huge advantage over your competitors.